Assalamu alaikum guys, my name is Hussain and I am from UET Texla. Today our lecture will proceed from the previous lecture, that is IFFT fast Fourier transform. In this lecture we will again move towards fast Fourier transforms basics, that we can convert our 8-point DFT into 4-point DFT into half, and then again into 2-point DFT into remain half. Why we are doing that? As we know that at 8-point DFT multiplication for the 8-point will be 64, and for the addition the formula n into n minus 7, if we put that, the addition will be 56. This means that the cost of multiplication will be more than the cost of addition. So that's why we will perform the addition, and now we will divide the 8-point into even and odd points, 4 of each points, and this will convert, and again the value of multiplication and addition will reduce, and this will make our system more efficient. And you can see now, by converting into the 4, the total number of the additions will reduce to 40 instead of 64 in the above 8-point DFT. And then again converted this 8-point into 2-point DFT, this will reduce from 640 to now 16. Now means that if we are converting the discrete Fourier transform into by using the technique of fast Fourier transform, we will reduce the multiplication cost as we move and divides. This is the formula, the final conclusion, that n square will be n log 2n. That will make the sense. This is the first example, and we will take them different values: 1 1 minus 1 2 0 1 minus 1 1 and 3. First of all, we will convert it by to the binary um, of the following numbers, and then we convert it into the even and odd, both of them, by dividing the values, and then by making this butterfly table, and we can see that the values coincide with give the result of 2 0 3 1 minus 2 0 and 3 and minus 3, and this will give us the final solution, which is a more component in DFT. Then we have an example of x of n, a value for the bit reversal x of n. We have two numbers, 1 and 1, so we calculate by using DFT, and we have the following circle. At 0 it will give value 1, and at pi it is minus 1, and this is, you can see that the given the results of x of 0 and giving the result of 2 x of 1, it giving the result of 0. And then you can see that from this we can conclude that we have the following ratios of w21, w24 and w48. Now moving towards our for next step, that is we will convert this 2 number graph into the 4 number graph. You can see here that this number is again converted: 2 0 3 minus 1 2 0 and 3 and minus 3. This will be used to solve it, and we will solve, and we will get the imaginary numbers by drawing the graph. Like you can see that at 0 it gives the 1, at pi by 2 it given the j, pi at minus 1, and minus pi by 2 at minus j, and these are the following answers for that. And then we solve it, and we will get the numbers after converting this 8-point DFT into 4-point DFT, 2-point DFT into 4-point DFT, and then we are moving towards the 8-point DFT. And you can see that its value, if we put there the result of the above 4-point DFT into this result, that is 5 minus j minus 1 j 1 3 j minus 5 and 3 j, you will get the final result of the answer. It will be 6 and minus 1 plus 5j, and like minus 2.21 plus j 3 to 3.21. These are final results. And then the next technique we will be used in this lecture, inverse Fourier transform. Again, the results coming from the previous question, we will start from that. This is the following result, and then we will start and dividing it into from 8 to 4 components. Then we divide it to 4 components, and then this give the result of 10 2 minus 2 10j, that is imaginary components, another. And then we will put in the following 4 point DFTs into the 2-point DFTs, and then you can see that the following result is given out: 8 minus 8 12 minus 8 0 0 minus 4j, like that. And then this result will give us the final result answers, that is the question of the previous question: 8 minus 8 16 0 minus 8 8 and 4, and this is giving the result in this form. And by calculating the frequency, if we ask to eliminate the 2k above elements, and then we have used this formula: delta f is equals to fs over n, it will be equals to 20k. So eliminating the term of 40 kilohertz, the putting the value of x1 x0 and x7, that will be again putting 0. This is an important technique. Then we will put the x0 value, x1 value and x7 value 0, because these components are less than 4 kilohertz frequency. We will require more than 4 kilohertz frequency. The remaining components will be required. Then again we will start discrete Fourier transform, and you can get the following results, and then we convert into the 4 from 2 to, and then we get the following two results. That's from the lecture part 1. And now moving towards the part 2. In part 2 we will take an example in which we have an signal element with the following inputs, and then we applying fast Fourier transform for checking that how much it will have the components form. It will be having the form 8 components. We will convert it into 8 components, their binary description. And now when we start with two component, converting into the two component ratio, and then we get the following result, and then this converted merging into the 4 elements, and then giving the ratio, and we converts 1 for each above and 0 for below. And then at the last, when we are converting into the 8, and then we are converting it into the 8 point DFT by taking inverse Fourier transform series, and then we get the result 1 for each. There is a circle for that, and then we shift 1 in the above question, 1 in on the extreme left side, and then we shift the 1 on the right hand side. We will check the result. What will happen? Overall they remain the same effect like in previous, and there is no big changing, but at last you can see that final result will be changed. In the above result you can see 1 1 1 1 1, but in this case there will be a change when 1 0.7 imaginary number minus j, then again repeat, then again another number repeat. This means that this is the final result, that when we are moving the results. Then there is a second thing we will start from that. That will be the sampling theorem, and you can know the how can we achieve it. We will multiply the signal impulse train with some signal, sinusoidal signal, and the recurrent, and this kind of the result, and this is basically sampling of the theory. And you can see that this is some kind of a signal having its conjugate part and its maximum frequency omega d. As we know that we will put it in the formula, that is convolution, because it is the basically multiplying the terms, that is we will convolving it. 1 over 2 pi is basically the ratio. We will put it into the following formula of the signal, that is it is a power signals, and you can see that the sigma ck e raised to power j by 2 is the formula, and the ck is basically coefficient, which is equals to 1 over ts minus ts by 2 to ts by 2 sigma, and this is the basically ratio. And then by deriving this equation step by step, we will putting the values of p, t and pw, and then we put inside of the previous equation of the x, and then we will get the result at the following form. You can see that this by convolving this result in this equation, and then this putting by this, and this we will get in, and then we applying the formula for this equation, which will be xc omega will be equal to delta omega minus k 2 pi ts. Then it will be like we can write also like this x omega, and then putting this value inside this, and this will be 1 over ts. So the final form for that is 1 over ts sigma from q minus infinity to infinity to that. Frequency will be in hertz, whereas 2 pi over ts will be omega, s will be in radians, and you can see that. So basically this is the signal, and this is the impulse train, and you can see that after multiplying this we will get a same sequence repeating after that, and here you can see the final result after convolving of the equation, that is 1 over t, and it is from x minus omega to omega s, and continuing and so on. And in the last, the frequency should be greater than fs, shifting frequency should be greater than the 2 time of the bandwidth. So the desired function, we have to multiply the graph with a low pass filter, and that's this is a result. Basically omega b should be less than omega s minus omega b, and this omega b is coming to this side and add it, and this will be not equal to that. If we not do that, these signals will be collide with each other, causing aliasing the effect. And we if increase the sampling frequency, it effect becomes negligible, but when we make it, our signal will lose the effect. So this is the, you can see the effect, and that the final cos omega t signals, and you can see that this is the impulse train for the cos omega t. That's it for today. We have learned fast Fourier transform, inverse fast Fourier transform in lab part 1, and in part 2 we learn about what is sampling theorem, and behind it we solve one example to check the answer, and in the last we will proceed in the next lecture in detail for the sampling theorem, that what are its properties and specification. For that, stay tuned.